Okay, good evening, everyone. We are through with the second law and the Exergy, and now we will proceed our discussion on the Exergy. Exergy is also known as the uh, availability. So, meaning this is the maximum work potential. If you have a device has a maximum work potential, so we will determine that. We know some processes like USUF, this USUF. Okay. So based on the general equation, this is Q. This is QCV of our system. This is QCV plus the summation of mass times this one, HI plus VI squared over 2G plus G ZI, right? And this is equivalent to M2 times U2 plus V2 squared over 2G V2 squared over 2 this is over 2 plus GZ2 1 minus the summation of mass 1 times this quantity U1 plus V1 squared over 2 plus G plus GZ1. Okay. This is the mass of your inside your control volume plus the mass that is leaving your control volume. This is HE plus VE squared over 2 plus GZE, right? Plus its work, the work of your control volume. You remember this formula, right? Or you already mastered this formula here. So now, if given a control volume here, if you have this, this is your control volume. This is your control volume, and you have this heat. This is QCV, and it will also generate work here. So you have the work W CV. Okay, and inside the control volume, this is your M2 times the U2 plus V2 squared over 2 plus G Z2 minus this is minus M1 times this U1 plus V1 squared over 2 plus GZ2. Okay, so we have a mass or energy that is entering, and you have this at the exit. This is the mass, this is the summation of your MI. This is HI plus VI squared over 2 plus GZI. That is GZI. And at the exit, you have the summation of this one, mass that is leaving, times the HA plus VA squared over 2 plus G ZE. Okay, so this is your control volume. You have mass, initial mass and the final mass, and it is you have energy that is entering and energy that is leaving. Okay, this is the real process, of course. No? If you have the SUF process here, this is the uniform state, uniform flow. This is your real process. Okay, now in order for you to relate this, for example, again, this is your control volume. Okay, so you have the quantity that is entering and leaving, given the mass and the mass at the inlet and mass at the exit. Okay, so you have now given a real engine. For example, this is your real engine. You tackle here a real engine. I will involve this in our discussion. This is your real engine. Okay, so you have your QCV here, and this one you have QCV. This is reversible, considering this is reversible. Okay, so here it will generate work also that is reversible work of your control volume, considering a reversible process. This is reversible. Okay, so here you have this one. Your real engine will also generate work here. Okay, so in total, you have this work reversible. Okay, so considering this is a reversible process, okay, this is a reversible process. Now, so this WC here, considering you have to consider a real engine. WC, we have Q sub O is equivalent to Q sub O minus QCV reversible. This is your QCV reversible. Now we will determine here the work of your control volume considering a reversible process. Considering a reversible process, this is QCV reversible, this is WCV reversible, and there are some students cannot join our meeting. Okay, I don't know what happened. So this is QCV here. This is reversible, of course, plus here the mass MI. This is HI plus VI squared over 2 plus G ZI. Okay, minus the mass, that is mass at the exit. This is HE. No, sorry. No, comma, it is plus. Okay, this is plus VE squared over 2 plus, this is plus, no, sorry, plus G Z E here. And this is minus M2 what happened? Okay, that is M2 U2 plus, or U2 plus V2 squared over 2 plus G Z2. Okay, minus M1 M1 H1 plus V1 squared over 2 plus this plus G Z1. Okay, so based on our knowledge and entropy, so we have here QH over TH is equivalent to QL. This is equivalent to QL over TL. QL over TL. Okay, so this is QO over T sub O. This is the integral of this quantity from 0 to T. This is Q integral of your Q CV over t here. This is reversible, and this is dt. Okay, so we substitute that in our equation for WC. WC here is TO, the integral of 0 to t times the QCV over t. This is reversible again. Then that is dt. This is minus QCV reversible. So we substitute that value in our last equation that we've here in the equation, this one, the equation of our WC. Okay, so now the work reversible here can be calculated as WC plus WCV reversible, where your WC is the work generated by your real engine, and the work reversible, the work of the control volume, considering a reversible process. Okay, so in order to know also its potential, we have what we call this irreversibility. This is irreversibility. This is denoted as I. This is W reversible minus W the work of your control volume. Okay, this is reversibility. We also discussed last time the some factors and that can affect the reversibility of a certain process. Like for example, you have the friction, the mixing, the chemical reaction, the thermal difference. Okay, so applying the second law here to determine the reversible work, of course, using the second law, wherein you have the uniform state, uniform flow process, which in first we consider in the very first of our discussion, UF. Okay, so we have M2, we have this entropy 2 minus M1 S1 plus the summation of the mass SE minus the summation of your M I SI. This is equivalent to the integral of your QCV over T from 0. This is from 0 to T. This is QCV over T. This is reversible, and it is dt. So now our WC here is TO, substituting this relation in here from our Q. So we have the TO. This is MO S2 minus M1 S1. M1 S1 plus the summation of your ME SE minus the summation of your mi si minus q cv, considering a reversible process. Okay, that is your wc now. Then we also like to determine the work reversible. The WC is the work generated by your real engine. Work generated by your real engine. Okay, so the work reversible, therefore, you will substitute the value of your WC in here. This is the relation WC plus WCV, considering a reversible process. Okay, now, so we substitute so WC is, you have TO MO S2 minus M1 S1 plus the summation of ME SE minus the summation of your MI SI. Okay, minus the Q CV, this is reversible. Okay, plus here, so the work of our control volume, considering a reversible process, would be this one. This is QCV plus the summation of your mass and this entering HI plus VI squared over 2 plus this GZI, right, plus, or this is minus this summation of the mass that is leaving your control volume. This is HE plus VE squared over 2 plus GZE, right? So this is of course minus this quantity M2 times H2 plus V2 squared over 2 plus GZ2. Okay, this is minus this one M1 times U1. No, this is not H2, this is U2. Okay, this is U2. U2. Okay, let's check on our equation here. Let's check. Okay, this is U. This is U in here. This is U1. Okay. U1 plus V1 squared over 2 plus Z1. This GZ1. Okay, you have this work reversible here and you have this WC. Okay, so this is applying the second law. This is the unsteady state or the uniform state, uniform flow. Okay, process. Okay, now we will reduce this equation is the general equation considering some conditions, like for example in this one we consider if for a system with the fixed mass, the one you have fixed mass system, meaning to say when we say fixed mass, the mass that is constant. Mass is constant in your control volume. Okay, mass is constant in your control volume. Okay, meaning to say your M1 is equivalent to M2. Okay, now so for a fixed system wherein we have a fixed for a system we have considering a fixed mass, so the summation of Mi Hi minus To this Si plus Vi squared over 2 plus Gzi. This is equal to 0, and the summation of mass this living, this is He plus minus To Se plus Ve squared over 2 plus Gze. This is equal to 0. So for a fixed mass, your M1 here is equivalent to M2, or let's just say this is equal to M, this mass inside your control volume. So considering a fixed mass for our system. Okay, fixed mass, the mass is constant at a given time. Okay, now we will for a fixed mass we'll determine its the work reversible from process 1 and 2. So the work reversible of our fixed mass, this is over M, this is work from 1 to 2. Okay, this is work reversible from 1 to 2. This is equivalent to this quantity U1 minus To S1 plus V1 squared over 2 plus G Z1 minus this quantity, this is U2 minus To, this entropy at the exit, Se plus V2 squared over 2 V2 squared over 2 plus G Z2. Okay, have this equation for a work reversible. Now if we are going to neglect the if you neglect the change in the kinetic energy and the change in or the delta P is equal to 0. It's equal to 0, meaning the potential energy, no? The PE and KE is equal to 0. So we will reduce the equation of our work reversible. It is now work reversible from 1 to 2 is therefore neglecting these values in here, the kinetic energy, the change in the kinetic energy, and the change in, or the change of potential energy. So work reversible, therefore we can simply rewrite that one. So this is by eliminating this one, so you have U1 minus TO S1, okay, minus this is U2 minus TO S2. Okay, now any questions so far? This is your work reversible considering a fixed mass system, or considering mass constant throughout the process. Okay, any questions so far? Yes. Okay, I don't know what happened sa ano siya pag-fix. Anyway, mutunga siya pero dili na siya maka sulod. So balik kita rang upat ano ron, kita rang 5 nga naa sa meeting. Na? Upo ka. Saan man na siya? May chat? Hindi daw kasud. Anong di man makasud? Anyway. Pautruha daw og yan. Pautruha daw sila og kining sulod. Sige daw. Balihog ko pautruha sila og sulod. Kung makasulod, kung okay na ba? Okay lang, okay lang. Pautruha daw sila og sulod kung maka-okay na ba? Please. Okay, para dili nila ma-miss po ang discussion. Siguro sa signal siguro na to, no? Saan man na nila? Okay, ano na lang, let's, yes, nag-record ko ni. Okay. Pero unfair mapod kung naa sila din sa dili sila kasulod. Let's end this meeting and this one. Okay. Nakasulod na ang uban. Thank you. So how about the others? I think daghan ang nagulat, no? Check it out. Those classmates of yours na still want to join our class, kindly tell them to join again. Just try. There's no harm in trying. lock out ang mga Gmail. So, ano nakasulod ba tong uban? Ang uban di masid kasulod. Okay. Very good. Namoy lain Gmail day. Sige lang, nga naman tong di mo makasud. Black ba ang inyong kuan? Gmail sa VSU? VSU to ninyo nga Gmail? Ang inyong gi-attempt og join? Okay, anyway. Yun. Okay, if you have other Gmail account, gamita lang na para maka-join mo. I don't know unsay na ito ba ano bakit ganung kuan dili magkasulod ang uban. Okay. Pero kining nakasulod na daan sa VS yung ninyo nga Gmail, no? Client and by losses and isa pa na. Tuyugon? Sa VS yung ganun nakasulod mo. Okay. Masagwa ka bantay ang gwardiya sa guard post, no? Kasulod mo. Anyway, joke lang. Wala pa yung gwardiya, nakasulod na. Sarado na kagabi na, oh. Anyway, let's continue our discussion. So, that's one for the fixed mass. I guess, musulod rito silang uban. And this is also recorded. Ato na siya i-post sa inyong let's post this inyong VSU e-learning. Okay, considering a steady state, steady flow. You have here a steady state, steady flow, or the SSSF process. So based on the formula that we've derived, this is M2 U2 minus TO S2 plus V2 squared over 2 plus G ZE minus M1. This is U1 minus TO S1 plus V1 squared over 2 plus GZ1, and this quantity is equal to 0. Okay, now the work reversible for the steady state, steady flow process would be, so this is the summation of mass that is entering, HI plus, or HI minus TO SI, or TO is the temperature of your outside surroundings, plus V1 squared over 2 plus G Z 1, or this is I mean this is I, Vi Zi minus this emission of mass that is leaving your control volume. This is He, He plus To Se is the entropy plus Ve squared over 2 plus this is Gz. Okay, so for the uniform state, for the steady state steady flow process, based on your knowledge in the term 1, the mass that is entering for steady state steady flow process is equal. The mass entering is equal to the mass leaving. Okay, so now the work reversible would be therefore this is work reversible. Work reversible here over m is from 1 to 2. This is work reversible. This is Hi minus To Si plus Vi squared over 2 plus Gzi. This is minus He minus TOSE plus VE squared over 2 plus GZE. Okay, here since this is per unit mass, so the mass leaving and entering is equivalent, so therefore we have this work reversible here. This is QCV plus the summation of mass entering. This is Hi plus Vi squared over 2 plus GZI minus the mass, the summation of mass leaving. This is He plus VE squared over 2 plus GZE. Okay, this is minus this quantity, minus that quantity M2 this is U2 plus V2 squared over 2 V2 squared over 2 plus GZ2. Okay, this is minus M1 U1 plus V1 squared over 2 plus GZ1. This is the in-your control volume. Okay, now this is for your steady state steady flow process, right? This is your work of your control volume. Okay, we'll summarize that one. So for uniform state, uniform flow process, you have you are to compute the irreversibility, since we already computed, or we already derive the work of our control volume, that is the work that is the maximum work. Okay, since it is considering reversible processes. So I is your irreversibility. You can measure that. This is the summation of mass, METOSE. This is the summation of mass entering TOSI plus M2. This is M2 TOS2 minus M1 TOS1. This is equivalent to QCV. Okay, so for that is for the uniform state, uniform flow. For the fixed mass, we have here fixed mass, we have this irreversibility. So here we have this summation of mass that is leaving, or this TO, this quantity here, SE. So this is equal to 0, right? Also this summation of MI TI TOSI is also equivalent to 0, since M1 and M2 is equal, and this is simply M. So if that is 0, or that is equal, so it would be 0 here. So you have here this irreversibility from point 1 to point 2, since your irreversibility is also a path function, wherein you have initial state and final state. So MTO, this is the delta, no, this is the S2, this one, this is the S2 minus S1 minus Q, what, Q from 1 to 2. Okay, that is for the fixed mass. And for the steady state, steady flow process, we have in here, this is our assumption here, this is M2, that TO S2, this is equivalent to M1 TO S1, right? So if that is equivalent, and therefore we have this irreversibility. This is the summation of METOSE minus the summation of MI TOSI minus the Q of your control volume. Therefore, you have this I here. This is we will factor out the TO in here. So here we have the delta of your entropy over dt inside your control volume. Of course, this is the summation of M E S E minus the summation of your MI SI minus Q, no, MI minus, we have here I d o s t maybe is I minus q. This is minus q cv over this t. Oh, this is your reversibility in here. So you will simplify that. This is TO. Your irreversibility would be the change of your entropy over dt. This is plus the delta S of your surroundings, right, over the dt. And this is your irreversibility in here, considering a steady state of flow process. Irreversibility. So we have the uniform state, uniform flow, the fixed mass, and the steady state of flow. Okay. Now, again, your TO is your temperature surrounding temperature, no? Surrounding temperature. That one. That's surrounding temperature. So the exam, especially it's a board exam, no? You are going to take your board exam someday. Hopefully, if you will pass this subject and all the subjects in the curriculum of the BSME. So if it's not specified, so you would take TO, or the temperature of your surrounding, as 25 degrees Celsius, or this is 298.15 Kelvin. If the TO is not specified. So since TO is the ambient temperature, or the surrounding temperature here, so so some examiners may assume that you already know what is the temperature of your surroundings. Let's just take a look. Maybe if you assume that is 28, this is okay. If you assume that is 40, that is okay. Okay. So if for uniformity sa inyong solution, you just take TO is equivalent to 25 degrees Celsius if that is not given in the problem. Understood? Gets? Okay. Any question? Any question? Okay na. So let's proceed na. So here we will proceed in our next topic. This would be the maximum. This would be the maximum reversible work. The question is how can you get the maximum reversible work? So here, if you have a device, we have a turbine. Okay. If you have a turbine in here, your turbine will generate work, considering that it's reversible. Okay. This is your point 1 and this is your point 2. Okay. So in order to we need to consider the maximum reversible work. We need to consider the surrounding. Okay, so given the surrounding, you have the V is equivalent to 0, and Gz also, and this T is equivalent to your outside temperature, and your P is your PO. Now, this is called the dead state. Why? Because your velocity is equal to 0. And through a dead state, you can be able to determine the maximum reversible work. We have the minimum reversible work, and we have this maximum reversible work. So anyway, this is just the work. We are going to maximize the work considering the temperature of our device or of any system given in the problem, or given in a real scenario, or in a hypothetical scenario. So this is this dead state, meaning there is no motion, that the velocity is equal to 0. Okay, this is just an illustration. So dead state is and we know that dead state is not real in the real world, no? So this is just an assumption, so that we can be able to analyze or determine the maximum reversible work that can be obtained by any device. Okay, now, so again, we will consider also these processes, of course, which are here already mastered since Thermo 1. So this is steady state steady flow process. Okay, what is the steady state steady flow process here? So we have this work reversible. This is the maximum reversible that we're talking about. So this is hi minus to si plus vi. Okay, sorry, tos i tosi, that is tosi. Where's that? Okay, tosi plus v1 squared. That is v1 squared v1 squared okay, tos I plus v 1 squared v1 squared. This is plus this plus plus gzi close parenthesis. This is minus he plus tose plus v squared over 2 plus g z e. So in here you have the work reversible, that is the maximum, no? Since we consider when we consider the surroundings, it is 0. You consider the surroundings. You have the surroundings. So your surroundings, you have your TO, you have your PO, okay, you have your VO, and you have your ZO. So HE is equivalent to HO, right? And your SE is equivalent to SO, and your VE is equal to 0, and your ZE also equal to 0. Okay, so the Exergy per unit mass, or Exergy or availability, those are synonymous. Okay, now availability, we will determine the availability. 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 So the availability per unit mass. Availability is the same as the Exergy, unit mass. Okay, this is the symbol here. This one, H minus TO S plus V squared over 2, of course, plus G Z minus, this is H O minus TO SO plus G Z O. Okay, that is GZO. Okay, that is for the steady state steady flow. Now I would consider a device, because for example you have a turbine in here. Okay, you have the turbine. And this is your inlet, this is your exit, and this is your control volume in here, and this is your work. Okay, so the work reversible here, this is the Exergy 1 minus the Exergy I minus Exergy at the exit. So the work reversible, therefore this is equivalent to the summation of M I and what, this availability or Exergy minus the summation of M E times this one. This is I and this is E. Okay, and that is for the steady state steady flow. So question, did you understand or gets ba ninyo ang subject matter? and that is why we need to go back, or we need to discuss the trigo. We have those in here. We need to discuss the entropy, okay, so that you can be able to grasp and understand here the what is availability. Okay, it's the same relationship, the same equation here, but there's some additional when we have this availability. Availability is the maximum potential work that can be attained for any device, because we consider a dead state wherein we consider that the velocity is zero, and it is dead, no? Dead state, no movement. So by that we can be able to determine the maximum, or the maximum reversible work that can be devised. Okay, you have a question? What is that? Pwede pabalik sa formula sa availability per unit mass. Okay. This is the formula here. The that is the availability per unit mass. So that one. Okay. This is its symbol here. Okay. Okay na ba? Okay, thank you. So now siguro wala na ko na ini I think I don't go beyond, no, sa atong coverage, or did I mention another topic? Okay lang siguro, no? So now we will continue. So this is for the steady state, steady flow, huh? Okay. Now if you consider here if you have a fixed mass, of course, if you have a system here wherein we have fixed mass, wherein our mass is the same throughout the process. Okay, so the work reversible from 1 to 2, since the work is a path function, so it needs to have an initial state and a final state. So here u minus to s, this is 1, okay, minus u2 minus to, it is tos 2 here. For this to be a maximum, if it must be in equilibrium with the surroundings. Okay, so for this work reversible to be maximum, it is need to be in equilibrium with the surroundings. Okay, so you have u2 is equal to u1, and you have this s2. Sorry, you have this s2 not the s1. Okay, so the work reversible, that is maximum, this is the maximum, right? This is u minus tos minus u minus TO SO. Okay. So we consider the surroundings again. Okay. So we'll proceed with this one. Work done. The work done. If you have the work done against the surroundings. So you have this work of your surroundings. This is P O, diba? V. This PDV, diba? So P O minus V. And this is the negative of M. Considering the mass, this is MP delta V minus VO. Take the negative outside na. Okay. Can you follow? Just interrupt no kung dili na masabtan. So the availability hindi na mawagi akong pen. Ano naman availability or the Exergy availability or Exergy per unit mass of the system. Here per unit mass of the system. So this is our symbol here. So this is the work reversible, the maximum of course, minus the work of your surrounding. Okay, so we substitute. So let us recall this formula here. This is the work of our reversible considering the maximum, since we consider we assume that it is in equilibrium with our surroundings, and the work done against the surroundings, we have this W. The work of our surroundings is the negative MP times the V minus VO. Okay, so we substitute that in here. So work reversible mass, so this is U TOS minus U sub O minus TO SO plus P V minus VO. Okay, so now we will simplify. So U plus PO V minus TO S minus this U sub O plus POVO minus TO S sub O. Okay, there is S sub O. Now, okay, so U minus U sub O, okay, plus PO V minus V sub O minus T O S minus S above. This is the availability here, or this is the Exergy. This is the Exergy. This is the Exergy here. This is the Exergy, or the availability per unit mass of the system. We consider the surrounding temperature. Okay, we're in your U sub O here, U minus U sub O. Recall your thermo 1 again. This is CVO, right, times T minus T sub O. Okay, so you have those V. So ganitong V, if you have an ideal gas, so RT over P. So our VO also, you have R, then you have T sub O. So next we consider the surroundings over P sub O. Okay, so now we'll just need to recall these relations. So this is S minus S sub O, this delta, this is CV ln T over TO. For this is the Exergy for is this applicable for gases? Of course, this is R ln V over V sub O. And your S minus S sub 1, this is CP what? ln T over T sub O minus R ln P over P sub O. Okay? Gets? Gets ba?